Greetings, Earthlings. I've been working on updating the schematics and the PC board layout for the video card of the Nova 445. Planning to do a second version of it, and that's because, well, I had to make some mods, and I wanted to add a little more functionality, and I wanted to move some functionality from the not yet designed disk controller board to make more room for the disk controller. So that disk controller board, I originally had in mind that it would have a real-time clock, interrupt handling, serial port, and a disk controller. It's looking like the disk controller is going to need a lot of real estate, so I'm moving the serial port to this board, and that will save me a lot of real estate. Well, how do I do that? You know, this isn't that dense a board, but it also has this cutout. And so what I'm doing is I'm eliminating that cutout, which means that this board will have to go underneath the main processor board, which is fine. It can do that. And I've also eliminated some things in the video control. I had started on some stuff for what they call read, modify, write control. This processor, this video chip, actually has a lot of smarts in it, and it can draw figures and stuff on the screen, but I'm not going to use any of that for this application. So I didn't need, for instance, these two chips down here. So I found room to add on here, in addition to the serial port, a sound chip. And so this is going to become pretty much the, call it the human computer interface card. And then the third card will be the disk controller, real-time clock, and interrupt control. And we'll call that the, operating system interface card or something like that. The one thing about the serial port here, I mentioned interrupt control is going on that third card, so it will not, there'll be no interrupt enabled for the serial port. It'll be strictly pulled I/O unless that third card is installed. I have a couple of spare pins on the connector here, and so I can route the necessary signals to that interrupt handler, which is to that third board where the interrupt handling is going to be. So before I zip off the order to JLCPCB, there were a couple of things I wanted to check. The first is the baud rate generator. Now, I used this same baud rate generator in the Stupid computer, which is a 12-bit homebrew computer, TTL-based, that I built a couple of years ago. But that shows some glitches, and I haven't spent any time trying to track down what's going on. Occasionally, escape sequences get mangled, and I have had people say, oh, it's the monitor you're using, because it's an old Televideo personal terminal. But I just wanted to make sure that I wasn't getting any glitches from this circuit, because I have another. So this is using a 74HC4060 and then a 74HC151 to select the specific baud rate. But the 4060 is the divider down from this 19.6608 megahertz clock, which gives me the serial clock, which is 16 times the actual baud rate. I have another chip. I only have one of them, and they're no longer available, which is a baud rate generator. It's a General Instruments chip, which was actually what people would have used back in the day, so, historically correct and all that. But I like this circuit, provided it works. So I've breadboarded it up, and I'm looking at it here on the scope. Oh, wait, new toy. Yes, I got this from Keysight, which means they checked it over. It's a used Agilent 6000 series oscilloscope. And the thing I liked about it is it has a 10 megahertz input on the back. So I can, and I have a 10 megahertz oven controlled crystal oscillator that I can use to kind of as a standard. I'm not running that right now, but I'm just running the internal clock. But anyway, that was one of the things I liked about it. It's 300 megahertz, 2 gigasamples per second. You know, equivalent cost-wise, I probably could have got a Rigol or Siglent new. Well, no, I think this was still less than that as a used thing, but not quite the functionality of a modern one. But still plenty for my needs. So I've got the clock generating here, and you can see this is a capture of the output signal. Let's see, what do we have here? Counter no edges. What? Counter no edges? What do you mean counter no edges? Oh, let's take the probe and I'll put it first. On the, I said I'll put it first on the crystal oscillator, and that's pretty sloppy. And but you can see 19.661 megahertz when it gets it. When I get the leads connected properly. It's even worse if I use the ground lead and the little clip. So I'm using these short leads, but even so, largely because of the breadboard, you can see there's some overshoot there and stuff, but that's probably good enough. And then when we look at the output, I'm going to put that there, and I'm going to put that there. Okay. Yeah, and you can scale that. That looks even better. It's awful noisy, though, up here and down here, and there's some overshoot on both ends. This is 614.4 kilohertz. This would be 38.8 kilohertz baud rate, which is the fastest it can go. And if I go to the slowest it can go, that's here. And that's 2.4 kilohertz, which is 150 bits per second. Anyway, I can zoom in on that. I'm not seeing any glitches. I'm seeing a little overshoot, and again, you know, I think that's mostly the breadboard, so I'm not going to worry about that. I'm seeing a lot of noise, which I'm also not going to worry about, because it's you know, not enough to cause a glitch, I don't think. And there's no glitches, you know, that would drop down. So this would be about 5 volts. If that's 0, that's about 5 volts there. So we'd have to drop down in the 3 volt range, or pull up into about the 1 volt range or so for it to be causing any problems. And it's not doing that. So I think this is okay. The other thing that I want to check is, well, when you read the data from the UART, that's an 8-bit value. And the same would be true if we're reading from the GPU chip, but probably more of an issue on the UART, because if I ever get to actually trying to run existing code, like Data General's RDOS on it, it may depend on this, whereas anything I write for that graphics chip is code that I write myself, so I could work around it. But it's only putting 8 bits onto the bus. So the other 8 bits are floating. And the question becomes, what do you see at the processor if you have floating inputs? What we want is to read all zeros in the high 8 bits and then the character data in the low 8 bits. And so I've got to find a way to make sure that happens. But first I wanted to just see with what it's using. What it's using as the buffer, which is actually on the processor board, is a, what is it, 74 ABT640, which is a CMOS chip. CMOS chips don't like floating inputs. But this is an advanced BiCMOS chip, so I don't know. But I'm going to breadboard that up. I haven't done that yet. Breadboard that up and see what it looks like. And then I may either have to drive those lines or add pull downs to it to make sure that I see zeros. I hate using pull downs, so don't want to do that. Okay, so I'm back, and I've put the 640 there. And you may ask, why are you using S74ABT640 in the first place? Well, it's because it's what I could find for that particular chip. It came in ALS, maybe F, and ABT640. And just in terms of tracking down chips, this is the one I was able to find. So we'll see how it does here. Okay, what we've got here, I've got the B. These are the B side, and it's the A side. So that's what we want to see. The B's would be floating. We're transferring B to A. It does invert the signal in passing it through. Okay, and so what I've got is B1 I've grounded, B2 I've pulled up, and the rest of the B's are floating. So we'll see that that'll be B0, or B1 rather. This is B2, right? And then any other one is floating, and it looks like maybe it floats low, so I might be lucky here. On the A side, so A1, so that's 0 on the B side, and that is 1 on the A side. It's high. A2 was 1 on the B side, and it's 0 on the A side. And B3 was floating on the B side, and it's 1 on the A side. B4, 5, 6, 7. So it looks like I may be able to get away with this, just leaving them floating. Again, the A side, which is what goes to the processor lines are inverted. So if we see a high signal here, that's a logical 0, which means when they're floating here, we will read them as a logical 0, and it should be okay. Unless the chip latches up on me or something.